Okay, so good morning. We were looking at projections and projections, general projection theorem in Hilbert spaces. So in the last class, I talked about distance of a vector or a point from a subspace in a general Hilbert space. So we wanted to project just like we projected in 3 dimensions. We projected a vector onto a 2-dimensional surface. In the same way, we could project a vector in general Hilbert space, which could be infinite dimensional, onto a subspace which is finite dimensional. Okay, so this we derived a formula, or we derived equations for computing the coefficients of the least square approximation, and so we are looking at what is called as the normal equation. I'll just go through over it very quickly. What we wanted was, we have a Hilbert space and we have this subspace S. S is a subspace of X is a subspace of S, and then we are given a vector u that belongs to X. A vector u is given to you that belongs to X. Now X may or may not belong to this subspace S. Okay, I want to find out the point in the subspace which is at the shortest distance in the least square sense from u. So what I essentially want to do is, so let's say S is equal to span of some basis vectors so these are linearly independent basis vectors. There are m basis vectors, and so this is a finite dimensional subspace. S is a finite dimensional subspace. I want to find out so any vector that belong to this subspace will be of the form alpha 1 a1 any vector that belongs to S will be a linear combination of these basis vectors. Okay, what I want to do is to find out alpha 1 to alpha m such that 2 norm of u minus or let's say 2 norm square. I want to minimize sum of the square of errors when it is finite dimensional. I want to minimize the integral. I want to minimize the integral if it is infinite dimensional space. I want to minimize this integral over the domain. This is 2 norm square, that means inner product of this vector with itself. This is the error vector. U is the original vector in X. This is the projection. This P here is the projection. P here is the projection, and then we want to find out a vector P that belongs to the subspace S, which is at a minimum distance from. So what I wanted to emphasize again and again, it's not different from, say, this is the point, okay, and this is my plane here, okay, this is 2-dimensional subspace, and this is a point. The shortest distance of this point is obtained by dropping a perpendicular. Okay, so what classical projection theorem in Hilbert spaces says is that the way to find this vector P which is at the shortest distance is to use the fact that this error vector E, that is u minus p. This is perpendicular to ai, I going from 1 to m. Okay, this error between the original vector and the projection, this error vector is orthogonal. Remember that orthogonality can be used only in the inner product space or a Hilbert space, and that's why we work with two norm or least square approximations. That's why least square approximations are so popular, because you can use orthogonality ideas. Okay, so this is the basic idea. With this, we derived what is called as a normal equation. This normal equation gave us way to compute the least square estimate of alpha 1 to alpha m, and that we constructed as follows. So we got this normal equation. This was a1 inner product of a2 a2 am. Likewise, okay. So using the fact that the error is orthogonal to each of the basis vectors a1 to am, we arrived at this equation. This equation is called as the normal equation in Hilbert spaces. This, when I solve this, these inner products, these are the inner products here. Once you compute this a1 to am, these basis vectors are known to you. You can compute their inner products. Okay, so this will be a matrix. What is the dimension of this matrix? This will be a m cross m matrix. There are m vectors. This will be m cross m matrix. This m cross m matrix is invertible. In fact, it is symmetric positive definite invertible matrix. You can check that. And then you can solve for alpha 1 to alpha m. You can get a least square solution. What you will get here is the least square solution of alpha 1 to alpha m. Okay, you will get the projection vector. Once you use this alpha 1 to alpha m, you get the projection vector onto the subspace S, which is at the least distance from U. Okay, so this is the best approximation of. Now I began in the working on this using finite dimensional spaces. I had derived a formula which said that A transpose A inverse theta. So this, in the finite dimensional spaces, this, just go back and have a look at what we have done. This will reduce to, the same thing will reduce to A transpose A. This will reduce to theta. This will reduce to A transpose U. In the finite dimensions, this equation will reduce to, okay, the matrix equation which we have derived earlier. So I am just extending the idea from finite dimensions to a general Hilbert space. Here I could work with any of the, see for example, I began my lecture last time by saying I have this vector ut which is a plus bt, and t belongs to 0 to 2 pi. Okay, t belongs to 0 to 2 pi. I want to find out an approximation pt which is alpha sin t plus beta cos t. I want to find out approximation alpha sin t plus beta cos t. Okay, let's say we can, so for the time being, let's take only two vectors. What are the two vectors? What is a1, a2 here? This is my a1 vector, this is my a2 vector, this is my a1 vector, this is my a2 vector. Okay, how do you find out alpha and beta? So what I have to do here to find out alpha beta, how do I set up the problem to find out least square estimates? So I have to find out sin t sin t, sin t cos t. What is sin t cos t over 0 to 2 pi? Can you do these integrals? What is the inner product defined here? How is the inner product defined? Inner product between some f and g is integral 0 to 2 pi ft gt. Inner product is defined here like this. Okay, inner product is defined here like this. So now we know that over 0 to 2 pi sin and cos are orthogonal. So this is 0, this is 0. Okay, if you notice, what we are actually deriving are the first two coefficients of the Fourier series. I am doing Fourier series expansion of ut in terms of sin and cos. Okay, the nice property of sin and cos over 0 to 2 pi with this as my inner product is that they are orthogonal. So this is 0, this is 0. I get a diagonal matrix. Solving for this diagonal matrix is very easy. It's very easy. It's not so difficult to solve for. So what is integral sin t sin t? It's pi. Inner product of sin t ut and inner product of cos t ut. So this is equal to pi, this is equal to pi, this is 0, this is 0. Okay, the least square estimate, the best estimate of, in the least square sense, in terms of sin and cos of this function ut in this particular case I have taken a plus bt. It could be, it need not be, you know, this kind of function. I can take, for example, ut to be any other complex function. I could take this as, you know, 1 plus 5t square minus 7t cube sin t. Let's say this is my function. Doesn't matter. This is a function, okay, in the space of, in the set of continuous functions over 0 to 2 pi. It's a continuous function over 0 to 2 pi. Okay, I want to find out best approximation to this function using sin and cos. Okay, I can go on. If here I have included only two basis vectors, well, somebody might say just using 2 is not sufficient, you want to use 4. Okay, in which case I would use sin t cos t, sin 2t cos 2t and so on. Okay, so the approximation could become more and more complex if you want. So I can have alpha 1 beta 1 plus alpha 2 sin 2t plus beta 2 cos 2t plus alpha 3 sin 3t plus beta 3 cos 3t. Let's say I want to develop an approximation like this to this problem. How will you do it? We just methodically apply this formula. Okay, now there are 6 vectors. The subspace, what is the subspace spanned? Subspace spanned by 6 vectors: sin t, sin 2t, sin 3t, cos t, cos 2t, cos 3t. We want to find out best approximation of the given function, okay, best in the least square sense. Okay, in the subspace spanned by these 6 vectors, what I do is I find out these inner products. Okay, I evaluate these inner products between 6 vectors. This gives me this matrix. On the right hand side, I have to compute inner product of the given function with each of the vectors. Okay, and when these vectors are orthogonal, actually what we recover is the Fourier series expansion, the Fourier coefficients. Okay, when these are orthogonal, you know, only the diagonal elements of this matrix will be non-zero. Okay, only diagonal elements will be non-zero. All the off diagonal elements will be 0 because orthogonal vectors inner products are 0. If I take an orthogonal set, why do we actually want to approximate something using an orthogonal set? That is because the projection problem, approximation problem gets very, very simple. Okay. Also, there are some other advantages like actually what you are doing here is you are, when you do this orthogonal projections, you are expressing a vector in terms of its orthogonal components. Why do we work with xi, yj plus zk in 3 dimensions? Because x is a component along, unit vector in x direction, y is the component along. Okay, they are orthogonal, they are not related to each other. Okay, they are not related to each other. The same way, what we are doing here is that we are expressing a vector in terms of a basis. Okay, we are projecting onto orthogonal basis. Now, the complete vector you can write if you take all, see, if I take a vector x which is given by 3 coordinates x, y, z. Okay, when will I get the entire vector? If I take all the 3 components together. In the infinite dimensional space, when will I get entire vector? If I take all the basis vectors and take projections along each one of them. Okay, if I take projections along each one of them, then I will get the Fourier series. I'll just write down this whole thing, it will become more clear. But there is one more thing I just want to tell you. See, these vectors, right now I have chosen them to be orthogonal. I have not chosen them to be orthonormal. If I choose them orthonormal, what will happen? Suppose these vectors are orthonormal. What is the property of orthonormality? Inner product is equal to 1, right? And inner product between ai, aj is 0 and with itself is equal to 1. What will happen to this matrix if I take orthonormal vectors? This will be identity matrix. If I take orthonormal vectors, to find out the projection, all that I have to do, okay, is to, okay, so the concept is not different from, I'll just leave this and come back there. So the concept is not different from, see, if I have this 3-dimensional vector, if I have 3-dimensional vector v belongs to R3, okay, how do you find out the component of v along x-axis? I take inner product of v with I is the direction. So I am talking here about, this is my ijk orthogonal basis for 3-dimensional space. Okay. If I take inner product of v with I, what will I get? I will get x component, right? I get x component. Inner product of v, y component is inner product of v with z, and z component is inner product of v with k, right? How do we write this vector? How do we express this vector? We express this vector as v is equal to xi plus yj plus zk, where I, j, k, let's put this cap here, let's say they are unit vectors. I cap, j cap, and k cap are unit vectors. Okay, but this writing is same as inner product v I plus inner product v j I could as well write this like this, right? This and this is same. You agree with me? Okay. Here, what we can do is that in a general inner product space, if you are given a basis, now this X is my inner product space or Hilbert space. Okay, is a Hilbert space, and I give you a basis. So this Hilbert space could be any of the Hilbert spaces that we have looked at. Okay, so need not be just finite dimensional. It could be any of the infinite dimensional Hilbert spaces that we have looked at, and then I give you a set of orthonormal bases in this. See, for example, I can create if it is 0 to 1, you know, I can create shifted Legendre polynomials which are orthonormal. Okay, I can create a basis which is shifted Legendre polynomials which is orthonormal, and I can use that to define a subspace. So in general, you are given a basis set. You are given a basis. I will call this as E1, E2, En. This could be a finite basis, this could be an infinite basis, depending upon what kind of inner product space you are looking at. Okay, if you are looking at set of continuous functions, twice integrable continuous functions, then this will be infinite basis. Okay, so I may have finite number, I may have infinite number of elements in my basis set. These are orthonormal vectors. What is the meaning of orthonormal vectors? Orthonormal vectors, which means Ei, Ej is equal to 0 if I is not equal to j, and this is equal to 1 if I equal to j. If I is equal to j, then this is equal to 1. These are orthonormal vectors. Their magnitude is 1 and they are orthogonal to each other. Okay, so this is the orthogonal basis. This orthogonal basis is same as ijk that we considered in 3 dimensions. Why do we like ijk in 3 dimensions? It's orthogonal basis, it's very nice. Okay, I can express any vector in terms of components along each direction. Okay, the same thing is true about any inner product space. Now, how do I express an arbitrary vector u that belongs to the inner product space? How do I express this vector in terms of these bases? How do I get those components? I can use I want to project. What I want to do? I want to project this vector onto the space spanned by all possible linear combinations of this. Okay, let's take there is an infinite set. Okay, so if you start writing the normal equation, what will be the matrix? Matrix will be I, because of orthonormality. This is 1 if it is diagonal elements will be 1, off diagonal elements will be 0. Okay, so by virtue of this, okay, you will get the coefficients. If you start writing the normal equation, you will get coefficients. You will get coefficients I into this vector, say alpha 1, alpha 2 and so on. This is equal to inner product of u with E1, inner product of u with E2 and so on. Because this is I on the left hand side. you have orthonormal vectors. Okay, the inner products are between I not equal to j are 0, inner product of with itself is equal to 1. So the left hand side is all I, and I which is of infinite dimension. Let's say if there are infinite vectors, I of infinite dimension. Okay, so these are the coefficients. How did we write the vector here? We wrote the vector v as v component of v along I times in the sense this is the direction I plus component of v along j times j and so on. Okay, same thing I can do here in the inner product space. I can write the vector u as inner product of u e1 plus inner product of u e2 plus, is everyone with me on this? Is this clear? I am just writing this vector u. Now I am not approximating. When I take the basis, when I take this e1, e2, e3, e4, en or e infinity, whatever it is, when I take this as a basis, okay, I am not approximating. It is equality. Okay, if you have infinite basis, you will get infinite sum here. So this is equal to sigma I equal to 1 to infinity u ei okay. Actually what I have written here is generalized Fourier series expansion of any vector u in terms of orthonormal basis in fact. Okay, so actually when you write this, just remember this, when you are writing this, you are actually writing Fourier expansion of v. You are writing Fourier expansion of v, okay, in terms of orthonormal basis. That's what you are doing. I am just using the same idea in any other space. Probably when you studied Fourier series for the first time in your second year or second year of engineering, yeah, you start wondering why. I mean, somebody comes and says, take this function and write it as sine and cos. What do I gain out of it? Okay, actually what you are doing is same thing as writing xi plus yj plus zk, what you do in 3 dimensions. It's nothing different. Same idea extended to any other Hilbert space, any other general space. What is nice about orthogonal basis? You know, you can look at individual components separately. Okay, you can look at individual components separately. It's very easy to work with orthogonal vectors. We know that in 3 dimensions, that's what we want in any other 3-dimensional vector space. That's what we don't want to do in any other vector space, which is a Hilbert space. It's possible only when you have inner product. You have definition of, you know, angle generalized. Otherwise, it is not possible to do this. That's why Hilbert spaces, that's why least square approximations are so important, you know, in engineering or most of the applications. Why we look at least squares? Why we use 2 norm all the time? Why not 1 norm? Why not infinite norm? Okay, because 2 norm comes tied up with angle, orthogonality. You know, everything that is nice in 3 dimensions. Okay, so this is generalized Fourier expansions. If I give you a general function, say a specific example of this would be the classical Fourier series which you study in second year of engineering is for the space x is for the set of continuous functions over either minus pi to pi, or we study over 0 to 2 pi, right? Square integrable functions over minus pi to pi or 0 to 2 pi. This is where you look at these expansions, and then we are given this basis vectors. Unfortunately, sine cos are not orthonormal, they are orthogonal. Okay, and if you remember, you get when you are taught this Fourier series, you get this, you know, ai is equal to 1 by pi integral. Remember this formula? ai 1 by pi, then 0 to 2 pi ft sine it dt, something like this, right? Where does this pi come from? this pi comes, why does this pi come? I mean, I used to have this problem when I studied this. Why suddenly put pi there? First of all, remember that this is nothing but inner product of ft sin it divided by inner product of sin it sin it. Okay, this is a normalizing factor 1 by pi, which comes because sin it is not an orthonormal vector. I want to get an orthonormal direction. So this is what it is. Okay, in this Fourier expansion, just look at how will you find the coefficients. See, this is my Fourier expansion. Okay, if I take inner product, of u, if I take u e j, what will I get? U e1, inner product of u e1 is 0, u e2 is 0, u e3 is 0, right? What will I get? You will get u ej. You will get u ej back because inner product of ej with ej is 1, right? Inner product of ej with ej is 1, and inner product of ej with ei, I not equal to j is 0. Okay, so all the terms in this series will cancel. Only one term will remain, that is projection along ej. Okay, so this very nicely ties up with your xi plus yj plus zk, which you know from 3 dimensions. Just remember that Fourier series is nothing but extending this idea into a. Okay, so far nice. So we have little bit diverted because we are not going to use Fourier series in this course, but Fourier series will be useful in the mathematical methods course. We will be looking at all kinds of Fourier series, you know, in terms of Bessel's function and in terms of some other familiar names will appear, but now they should fall in a place, you know, you should be able to see them in light of this general development of what is projections onto orthogonal spaces. Yeah, not subspace in R3, 3-dimensional subspace in R4. R3 would be a, yeah, perpendicular will lie in R4. Perpendicular will lie outside R3. Perpendicular will lie outside R3. Okay, so actually you are splitting a vector into 2 components, one along R3, one orthogonal to R3, which will of course lie in the general space. So this Fourier series is just a side note. It is important here, of course, but it's more important when you develop analytical solutions. Okay, so before we move on, I still not coming to applications to boundary value problems or PD. But before I move on, I want to explain something which is very important. Well, I have been telling you that, using polynomial approximations, okay, or polynomial interpolation, high dimensional polynomial interpolation is the problem. Same thing is true about actually polynomial approximations. If you start developing a polynomial approximation, which is, even if you have a large data set, if you have a polynomial approximation of this form, I have a function ft in which belongs to set of continuous functions over 0 to 1. Okay, and then I want to develop an approximation pt, which is, alpha 0 plus alpha 1 t plus alpha 2 t square alpha m t to power m. I want to develop this approximation. Okay, so how do I go about doing this? What are the basis vectors now? 1 t t square up to t to power m. Okay, I should set up the normal equation. how should be the normal, say my inner product here, my inner product is defined as 0 to 1 ft, my inner product is defined like this, okay. Well, there are two ways of looking at this problem. So let's say I know the continuous function over the entire domain, then I can approximate. The other problem that we have looked at earlier is, if you know this function at the finite number of points, okay, if you know this function at finite number of points, let's say n points, then it's the, we took this not ft, we took this ut. If I know u at finite number of points, then I found that formula, right, A transpose A inverse, that least square approximation formula, which can be used to, okay. This is knowing the function at every point. If I know ft, let's say ft is some function like t cube plus phi sine t or whatever, okay. So this is a function which I know over the entire domain everywhere, and I want to do an approximation. Well, so just to give you an insight why polynomial approximations are ill-conditioned, I kept on telling you that polynomial approximations are ill-conditioned, high order polynomial approximations. That's why you have to do in orthogonal collocations, we do piecewise polynomial approximations. We have these spline functions. So spline is fitting a low order polynomial by dividing the entire region into smaller segments. Okay, why we do all this business? So that's why now I want to explain you through this. Okay, so the question is now here, classic problem. I want to develop a mth order polynomial approximation. Now, what I know from Weierstrass theorem is that I can develop an approximation arbitrarily close to the function. See, this only tells you there exists a polynomial, which is, it doesn't tell you how to reach that polynomial. How to find is a different story. Okay, Weierstrass theorem only gives you existence. Now, when it comes to actual computing, there can be trouble unless you do some smart tricks. Okay, so what are the smart tricks? We'll come to that. Okay, so let's first look at this problem. Mth order, m is, let's say, large. I want to have some 10th order polynomial fitted here. Okay, and my ut is, let's take some ut, which is phi t square minus 7t cube sine t. This is the ut. I want to develop a 10th order polynomial approximation of this function in the least square sense. What is the meaning of least square sense? That means the two norm of difference between ut and pt should be smallest. Okay, we know that this can be found by using normal equation. So we go about finding out this inner products. So my inner product is 1 with 1, then 1 with t, 1 with t to power m, right? I am constructing the normal equation. Okay, I want to estimate least square estimates of alpha 1 to alpha m. Okay, then sorry, t with 1, t with t, and t with t to power m, and so on. So this times alpha 1, alpha 2, alpha m, and then how do I get the right hand side? Inner product of 1 with my ut, inner product of t with ut, and so on, inner product of t to power m with ut, and classical projection theorem tells us that if you solve this, you will get alpha 1 to alpha m. Okay, now let me tell you what is this integral. Well, these integrals may not be that difficult to evaluate, right? Because polynomial integral 0 to 1, okay, you can actually write a general formula for this. So if this matrix, this matrix, in my notes I have called this as H matrix. This is m plus 1 cross m plus 1 matrix. There are m plus 1, oh sorry, there are alpha 0, alpha 1, right? We start with alpha 0, alpha 0, alpha 1, not alpha 1, alpha 2, alpha 0, alpha 1. So this is a matrix which is, this matrix is m plus 1 cross m plus 1, matrix is m plus 1 cross m plus 1, okay. What is the element of this? So ijth element of this is given by 0 to 1 t to power I plus j minus 2 dt. This is equal to 1 upon I plus j minus 1. Well, why I have called this H will become clear soon, because this, what you get here is a famous matrix called Hilbert matrix. Okay, you can show that elements of this matrix, see these are inner products of t square, t cube, t4, t to the power 5. So I have just given a formula for general ijth element of this. You can very easily verify this, you will get this. Okay. Now, if I actually compute this, and then fill in the matrix, okay, the matrix that I get here is like this. It's a very, very nice looking matrix, 1 by 2, 1 by 3, 1 by m, 1 by 2, 1 by 3, 1 by 4, 1 by m plus 1, 1 by m, 1 upon 2m minus 1. This matrix is very, very difficult to invert. It's a highly ill-conditioned matrix. Now yet we have to define what is ill-conditioned matrix. We have to wait a little bit for defining ill-conditioning formally. Okay, but what you get here is a matrix. Okay, just to preempt what it means is that this is a basically, first of all, remember that this is a symmetric matrix. Okay, this is a symmetric matrix. Not only that, it's a positive definite matrix. Okay, this follows from the fact that this is actually what we have obtained in the case of projection. This is a projection matrix. This is obtained by projection matrix, is obtained from projection matrix, is related to the projection matrix. So this is actually a symmetric positive definite matrix, but it is highly ill conditioned because the eigenvalues of this matrix are very, very strange. The ratio of the highest eigenvalue to the smallest eigenvalue, okay, which is what for a symmetric positive definite matrix, which is what will define ill conditioning, we'll see this later systematically, is so large that computations become impossible, very, very difficult. Okay, so Hilbert matrix more than 4 or 5 m, that is third or fourth order polynomial, becomes difficult to invert. Okay, if you ask MATLAB to invert Hilbert matrix, it will give you some junk and say that don't believe the results. Okay, it will tell you that this matrix is ill conditioned. It will say it in a nice way, not it will not tell you don't believe the results. It will say that the solution may not be reliable. Okay, this matrix is highly ill conditioned. It will give you a number, R conditioning is equal to something. When you don't know when you are not done all this theory, you just tend to ignore MATLAB is giving something. Very, very important message that your results could be completely unreliable. Now to get alpha 1 to alpha m, I need to invert this matrix. Okay, but if this matrix is highly ill conditioned, the inverse is unreliable. If inverse is unreliable, alpha 1 to alpha 0 to alpha m calculated are unreliable. Okay, and then you are fitting a wrong polynomial not because your formulation is wrong, but you just cannot compute properly. There is no way of computing. You are stuck because this is an ill conditioned problem. Okay, this is an ill conditioned problem, but well, if you are smart enough and done this course and still remember things that I have taught you, you will say, well, that's not the way to go. I don't want a nil condition matrix here. Okay, so if I want to do polynomial approximations, what I'll do instead is, instead of using this raw polynomial like this, I would choose to use orthogonal or orthonormal polynomial. Okay, on 0 to 1, what is the orthonormal polynomial that we have constructed earlier? Shifted Legendre polynomials. Okay, so instead of developing this approximation, see this, if you want an equivalent of 3 dimensions, what you are doing here is you are trying to express a vector in terms of vectors which are not orthonormal or orthogonal. See, a given vector, if I give you one vector, say this one, okay, I can choose to express this in terms of 3 orthogonal components, or basis need not be always orthogonal. Basis can be any 3 linearly independent vectors. Okay, so see, the basis need not be like this. Even basis is like this, 3 linearly independent vectors. Okay, but if the 3 linearly independent vectors are something like this, which are very close to each other, you may have trouble expressing this any vector in terms of these 3 vectors. Just because they are linearly independent doesn't mean they are convenient. Okay, orthogonal vectors are convenient, because you can express them in a very nice manner. So what you would do instead of using this polynomial, you would say, I'll express this Pt as alpha 1, say L1t plus alpha 2 L2t alpha m LMT. What are these LM? These are shifted Legendre polynomials. Okay, I don't have to worry here now about the order I take. Why I don't have to worry? Because when I use shifted Legendre polynomials, I am not going to get the Hilbert matrix. By the way, in MATLAB, if you want to play with Hilbert matrix, just use command HILB and give into the into bracket the dimension you want. HILB 5 will give you Hilbert matrix of 5 cross 5. It will generate this matrix, same matrix. Okay, and just use inverse of that Hilb. Okay, it will crib that this matrix is ill conditioned. Try to multiply inverse into that matrix. MATLAB is fairly good till 12th, H12, it does a very nice job. But beyond H12, that is 12 cross 12, it starts breaking. Okay, so amazing that even for so highly ill conditioned matrices, it's able to do it. Now, okay, if I use the Legendre polynomials, what will happen to this matrix? This matrix will not be a full matrix, because, okay, let's call them, instead of alpha 1, alpha 2, let's call them some other number, so you'll get confused otherwise. Say beta 1, beta 2, some other, the coefficients are different, because the basis has changed, the coefficients are different. So now, if I want to find out beta 1, beta 2 to beta m, I have to take here inner products. Inner products will change. This will be L1u, this will be L2u, and this will be LMU. Now what about this matrix? What we know is that for shifted Legendre polynomials, okay, inner product of Li Lj is equal to 0 if I is not equal to j. What will happen to off diagonal elements? 0. What will be the diagonal elements? If I take orthonormal, 1. Okay, this will be just 1, 1, 1, 1. This will be a 0 here. This will be a 0 here. Right? I don't have problem of. So if I want to develop a high order polynomial approximation, okay, it is easier to go through the route of orthonormal polynomials than to use the raw, 1t, t square, t cube, t to the power 5 and so on. Is it clear? Why we are obsessed with orthogonality? Why we want orthogonality so much in every application? That is because of this nice property. If I take shifted Legendre polynomials which are orthonormal, this matrix, which in earlier case was the Hilbert matrix of highly ill-conditioned, I couldn't invert. Now see, this is the best matrix. There's no better matrix to invert than the identity matrix, right? So you get identity matrix, okay, you get the projections, and now there is no problem with what order you go. Okay, so it's not that you are not developing a higher order polynomial approximation, except you just turn around, change the basis, you get much better solution. Okay, you get much better solutions. That's why we always want to work with orthogonal polynomials. Now this orthogonal business will form, we looked at orthogonality, we looked at roots of the orthogonal polynomials in orthogonal collocations, right? So this, in this case here, if I use orthonormal set approximations are, just taking inner products with the vector. In fact, what you have done here is find out the Fourier series coefficients. That's it. This is conceptually same as writing a vector v as xi plus yj plus zk. That's all you have done. That's all you are generalized to any other dimensional space. If you remember this, that Fourier series is nothing but xi plus yj plus zk extended to any other space. That's enough. Okay. So now you know how to make approximations. Not only that, you know how to make good approximations. You can make good approximations if you use orthogonal polynomials. That's why we are concerned about generating orthonormal series, orthonormal functions, orthonormal bases, and so on. Okay, so the next class we'll now start with the with two things. One is how is least squares used for developing different engineering models. I'll briefly go over that in the beginning, and then move on to using these methods for discretizing ODE boundary value problem or PD and so on. So this will lead to so-called Galerkin method or finite element methods, FEM. You may have, I'm not going to do full of FEM because that will consume rest of the semester. I'm just going to touch the tip of the iceberg and say that this is what it is. Rest is for you to discover. Okay. So we continue in the next class about more applications of orthogonality.